In this video, we will be looking at the various equations of lines in R2. So the first way, which we've seen since grade 9, is the slope-intercept form, y equals mx plus b. We know m is our slope and b is our y-intercept. The next is your standard form, which looks like every component, the x, the y, the constant, everything's all to one side. Ax plus by plus c equals 0. This is also called the Cartesian or scalar equation. Now, there is an important property related to this Cartesian form, and I will talk about it momentarily. The third equation is the vector equation of a line in 2D. And the vector equation of the line is vector r is equal to vector r naught plus the parameter t times vector m, where that parameter t is any real number. Now, if you look at what we have here, it's the vector addition of two vectors. I'm going to start with vector m. Vector m is just the direction vector. So this is a vector that is collinear to your line or parallel to your line. So looking at the line that we have on the left here, I'm going to draw a vector starting from the origin that follows this line as best as I can. So here we are. This is the direction vector m. Vector r naught is a vector that begins at the origin and will connect to any point on the line. For example, let's pick randomly this point here. This is vector r naught. Okay, so a vector created by the origin with a point on the line. So now let's see how that connects to the line itself. So we know what resultant vectors are. If I were to add, let's say, the direction vector with this new position vector from the origin to the point on a line, and I created my parallelogram, here's the resultant vector. And this resultant vector will begin at the origin and it will connect to another point on the line. Now, the reason this equation can represent any single point on the line is because I can multiply my direction vector by any scalar value and it will modify the shape of this parallelogram to create a different resultant. For example, let's say I doubled the direction vector. Well, now this is my resultant vector, ending at this point on the line. So as you modify that parameter, you will be able to create these new vectors that start at the origin and end at every single point on the given line. Now, to go hand in hand with this vector equation, we can also write a parametric equation. Now, notice in the vector equation that the direction vector is represented by this vector AB, and this other vector that represents the vector from the origin to a point on the line is represented by x naught, y naught. So, our parametric equation will just split up those x and y components. So x will equal x naught plus the a value that is multiplied by t. And the y is equal to y naught plus the b value times t. And in both of these parametric equations, t is an element of all real numbers. So the vector and the parametric equations do go hand in hand. And now finally, going back to that Cartesian equation, the coefficients of x and y, so the a and the b value, actually do have a special property associated with them, and it's that the normal of the line can be represented by A and B. And what is the normal? The normal is the vector that is perpendicular to the line. So if you look at the line on the left here, the normal would be this vector here. Okay. Now, the normal and the direction vector do have a nice little connection here. If you know your direction, your normal will have that same idea as an opposite reciprocal in slope, which means you're going to flip your x and y components and change one of the signs. Because at the end of the day, if you look at this direction vector and think of slope, rise over run. If your direction vector is AB, rise is the vertical, and the vertical component is B, and run is the horizontal component, so A. So if you look at your direction vector, you actually have your slope right there, B over A, as your rise and your run. And now if I want a perpendicular slope, so an opposite reciprocal, that would be negative A over B. And if I write that as a vector, and that's going to be our normal vector because it's perpendicular, it doesn't matter where you put the negative, either component is fine, but your x component is the run, so B, and your y component is the negative A. So notice our direction vector and our normal vector. And that normal vector is right there in the Cartesian equation as the coefficients of x and y. So let's actually try some examples out. A line passes through the points A, 2, 5, and B, -1, -4. Determine vector and parametric equations to represent this line. Well, the first thing we need to do is find a direction vector. So direction vector M. I'm going to say my direction vector is just going to go from point A to point B. Okay? And we know how to find the vector between 2 points. So -1 subtract 2, -4 subtract 5, and that gives us -3, -9. Now I can use this for my equation, or I can simplify this vector to a more reduced form. So I can also use 1, 3 if I were to divide all of the components by -3, and then those numbers are nicer to deal with. But I can use either one, because at the end of the day, the direction vector will get multiplied by a parameter anyway, so it doesn't matter which one you use as long as the vectors are collinear. And then for my other vector, this vector is the one that starts at the origin and goes to any point on the line. And I have 2 points on that line, so I can use A or B. I'm going to use A. So this vector is going to represent the vector from the origin to A. So 2 minus 0 and 5 minus 0. Okay, now we have our vectors. Here is our vector equation. So R0 plus T times the direction vector. I'm going to use the simplified one, where T is an element of all real numbers. And the minute you have your vector equation, you can also write your parametric equation. So for x's, we have 2 and 1 times t. And for the y's, we have 5 and 3 times t. And again, for both of these, t is an element of all real numbers. Now, using these equations, we can determine our intercepts, or if a point exists on the line, or any point on the line, really. So the first question here is, what are the coordinates of the points that cross the x and y axis? So it's asking for the x and y intercept. For an x-intercept, we know that y equals 0. And lucky for us, we have this nice parametric equation that says y equals 5 plus 3t. So let's set that equation equal to 0. And when we do that, it will allow us to solve for the parameter for that x-intercept. And once we have t, we can sub it in for x, and then we'll have our x-intercept. So t is equal to -5/3. And now that I have that, I'm going to plug it in for x. 2 plus t, get myself a common denominator, that would be 6/3 minus 5/3, that's a third. Okay, so when y is 0, x is a third, there's my x-intercept. Now I'll do the same thing for the y-intercept, but for that one, we're starting with x equals 0. So I'm going to set the parametric equation for x equal to 0, bring that 2 over, and I get t equals -2. So the y-intercept occurs when the parameter is equal to -2. 5 plus 3 times -2 is -1. So our y-intercept is 0, -1. Finally, determine the Cartesian equation of the line. Now, we already know our direction vector from above. It was 1, 3. So if you know your direction vector, you also know your normal. Your normal is going to be flip the x and y's, so 3, 1, and change one of the signs. Whether it's the x or the y, it's up to you. So I'm going to do 3, -1. Because if I were to write this as a slope, the direction vector would be rise over run, so y over x. The opposite reciprocal would be -1/3. And that's exactly what the normal is. All right, now that we have the normal, we can replace those values in for a and b. So this is what my Cartesian equation looks like right now. I don't know the constant, but I have the other pieces of information. In order for me to find the constant, I'm just going to use one of the coordinates that I know exists on the lines, and then I'll isolate for c. So I'm going to use the point 2, 5. So 3 times 2 minus 5 plus c equals 0. Well, that's going to be 1 plus c equals 0. So the constant must be -1. So here is our Cartesian equation. Now, this does connect nicely to y equals mx plus b, and I'm just going to do a little side work with y equals mx plus b just to show how that Cartesian equation and the normal relate. So with the direction vector that we knew from before, the slope was 3/1, right? So that means in y equals mx plus b, we would have y equals 3x plus b, and just like in grade 9, plug in the point you know. So again, I'm using 2, 5, and isolate for b, for that y-intercept. So that's 6, bring the 6 over, and you get -1. So here's your equation in y equals mx plus b. And if I want that Cartesian equation, I just bring the y over to become -y. And there it is. So here is the slope and the direction vector, but the minute it's rearranged, 3 and the -1, it matches that opposite reciprocal slope, and as a result, that is the normal of the line. All right, let's try another example. A line can be represented by the parametric equations x equals 2t minus 3 and y equals -3t. Does the point 1, 6 exist on the line? Okay, well, x is 1, y is 6. If that point exists on the line, if I were to replace that coordinate into x and y and isolate for t, they would share a common t value. So let's see if that's the case. So 1 is equal to 2t minus 3, and 6 equals -3t. And now let's isolate for t. That's 4. Divide by 2, we get t equals 2. For the other one, we divide by -3 and we get -2 for t. So if our parameter is 2, the x-coordinate is 1, but to get 6 for the y-coordinate, the parameter would have to be -2. So this is not on the line. In order for it to be on the line, if I plug in a certain t value, I will get a specific point on the line. But here, the t's are different. Find 2 points that do exist on the line. Well, pick whatever parameter you want. So let's say t equals 1, t equals 2. Well, if t equals 1, x is going to be 2 times 1 minus 3, which is -1, and y will be -3 times 1, which is -3. Okay, there's one coordinate. The other, 2 times 2 minus 3 is 1, and -3 times 2 is -6. There's another coordinate. Okay, determine the vector equation of the line. Well, if we already have our parametric equations, then we can recreate the vector one really nicely. Now, something that might be helpful is to just rearrange this parametric form. So we know we want the vector that represents the coordinate on the line, so from the origin to the point first, and then the one with the parameter after, the direction vector. So I'm going to write my constant first, and then my t component. Y doesn't have a constant, but it has the t part. So here's r naught, and there's your direction vector. So -3, 0 plus t times the direction vector. Does the line -5, 3 plus s times -4, 6 also represent this line? Okay, well, number one, we need to check our direction vectors. If these direction vectors are collinear, then there's potential. It means the lines are parallel. That's a starting point. So can I take 2, -3 and multiply it by a scalar to get -4, 6? Yes, I can. I can multiply it by -2. So this means the vectors are collinear. The lines are parallel. Now, in order to see if they're parallel and distinct or coincident lines, we need to see if they share a point. If they share a point, then it's the same line. If they don't share any points, then they're parallel and distinct. So I'm going to take this point here, -5, 3, and see if it exists on this line, and I'm going to use the parametric equations. So -5 equals -3 plus 2t. I bring that -3 over, divide by 2, and I get -1. And here I set y equal to 3, divide out the -3. It's the same t value. They share a point. The lines share a point. Therefore, these are the same line. If they did not share a point, then our lines would be parallel and distinct. All right, for the next one, let's determine the Cartesian equation of the line. So we had our direction vector as 2, -3. So the normal, if we flip the components and change one of the signs, we'll get 3, 2. Because flipping it would be -3, 2, and then I took the -3 and turned it positive. I can't change both signs, otherwise the lines will not be going in opposite directions. Okay, now that I have the normal, I know my equation will be 3x plus 2y plus c equals 0. I'm just going to use one of the coordinates that I know is on the line, And I know that negative 3, 0 is on the line. So that's negative 9 plus c. So c equals 9. So our equation is 3x plus 2y plus 9 equals 0. Now, I like this way. It's pretty straightforward, but another way you could have found your Cartesian equation is by using those parametric equations. If you isolate for t in each of your parametric equations, then you can set those equal to each other and then get it into standard form. So here's the first one. I'll bring the negative 3 over and then divide by 2. So here's what t is equal to from the first one. And then for the second one, I'm going to divide by negative 3. And here's what t is equal to from the second parametric equation. T has to be the same value for any given point. So I can set those t's equal to each other. And now I can just cross multiply. So I have negative 3 times x and negative 3 times 3 equals 2 times y. And now I'm just going to rearrange this. I'm going to bring these terms over to the right because I like to have the x term with a positive coefficient. So 3x plus 2y plus 9. And we get the exact same thing. All right. Now we can graph our line. And we can graph our line using our knowledge of slope and the y-intercept, because if we know our direction vector is 2 over 2 and negative 3, then the slope would be negative 3 over 2, y over x. And we already know a point that is on this line, negative 3, 0. It's not the y-intercept, but that's okay. I can pick any point on the line and just start applying my slope to it. So I'm going to go down 3, right 2, down 3, right 2 a few times. I'll connect those dots. And there's my line. What do you notice about the slope and the Cartesian equation of the line? Well, the slope is the opposite reciprocal of the normal, so the 3 and the 2, which we've already discussed. All right, next example. The line L1 is negative 5, 2 plus t times 1, 6, where t is an element of all real numbers, is the given line parallel to the line defined by x equals 2 minus 2s and y equals negative 7 plus 12s. Well, to see if two lines are parallel, we need to compare their direction vectors. So I'm going to write the vector equation of this second line. So the constants are 2 and negative 7, so that's r naught. And the direction vector, negative 2 and 12. So we need to check if 1, 6 and negative 2, 12 are related. So can I multiply 1, 6 by a value? I'll just write k to get negative 2, 12. No, I can't because the 2 is negative. If it had been positive, then yeah, I could say k is 2. But this isn't going to work. And if I wanted to show my work, I could say 1k is equal to negative 2 for the x components. 6k is equal to 12, giving a k value of 2. These are different. So therefore, the lines are not parallel. Determine the parametric and Cartesian equations of L1. All right, the parametric, negative 5 plus 1t, 2 plus 6t. So just distributing that t in and combining the x's, combining the y's. For the Cartesian, if the direction vector is 1, 6, the normal is going to be 6, and then -1, or -6, 1, whatever you prefer. So this is what we know about our Cartesian equation. I'm going to use -5, 2 in for x and y to solve for c. So that's going to be -32 plus c. So c is +32. And there's our Cartesian equation. Determine a vector equation of the line that is parallel to line 1, so it has to have the same direction vector, and passes through the point 4, -1. Well, the only thing that's going to change is that r0. There it is. But the direction vector, we will keep. Determine a Cartesian equation of the line that is perpendicular to L1 and passes through the point 6, 2. So the normal of line 1 is 6, -1. If I want to be perpendicular, then the normal of the second line will have to be like an opposite reciprocal. We're just not taking a reciprocal. We're just flipping the x's and the y's. So there's the normal of the second line, which is actually the direction vector of the first line, which makes sense because direction vectors and normals are perpendicular. So we have x plus 6y plus c equals 0. X is 6, y is 2. That's 6 plus 12, which is 18. And when that moves over to the other side, c is -18. And there's the Cartesian equation of that perpendicular line. Given 2x minus 5y plus 8, determine the vector and parametric equations of this line. So we know that the normal of this line is 2, -5, which means the direction vector must be 5, 2. And the only other criteria I'm going to need here is a point on this line. And I can pick whatever I want. So just looking at it, I'm going to say I want y to be 0. And if it is, then this is what I'm left with. X equals -4. There's a coordinate, -4, 0. So we have that r0, -4, 0, plus t times the direction vector. And then for the parametric, x equals -4 plus 5t, and y equals 0, which I'm not going to write, is 2t. And for all of these, t is an element of all real numbers. Determine the value of k so that the following two lines are perpendicular. Well, if two lines are perpendicular, their direction vectors are perpendicular and their normals are perpendicular. And the normals are k2 and 3, -4. Now, what do we already know about perpendicular vectors? Their dot product is 0. So the dot product of these normals should be 0. So what is the dot product? 3 times k plus 2 times -4 equals 0. Isolate for k, and k is 8/3. All right, final little topic here. We can find the angle between two lines using our knowledge of the dot product. If we take those direction vectors and think about our knowledge of the dot product, we can isolate for cos theta. So if we take the dot product of a dot b, but in our case it's going to be the two direction vectors, and divide that by the magnitude of the direction vectors, we will get cos theta, and ultimately take a cos inverse to get our angle. So for line 1, the direction vector, so I'll just say m1, is -1, 3. For the second line, I'm not given the direction vector, I'm given the normal. And the normal is 3, 2, which means the direction vector of the second line is 2, -3. Now, let's get ready to find our angle. So, the dot product is going to be 2 times -1 plus 3 times negative 3 over the two magnitudes. So we have negative 1 squared plus 3 squared for the magnitude of the first direction vector, and then 2 squared plus negative 3 squared. So that is negative 11 over the square root of 10 times the square root of 4 plus 9 is 13. We can take a cos inverse of that fraction to get approximately 165 degrees. And that would be the angle at the point of intersection of these two lines. And that's it for our equations of lines in R2. So the vector and the parametric equations require our direction vector and a vector created by the origin to any point on the line. The parametric is just coming from the vector equation, just those x, y components. The Cartesian equation is just our standard form, but now we know the coefficients of x and y represent the normal. And there we are.